What's up everyone, this is Nate Davis. This is a continuation of my update class, 2019 update class. This slide presentation is provided by Tech Help. Tech Help training provides the slides. This is a how to use a lab scope training. Now we're going to talk about known good waveforms. Okay, so welcome to the class, so let's get to it. We're going to talk about known good waveforms on a single channel lab scope. This is a waveform of an AC signal, permanent magnet. You can see here, this is the zero line here. From 0, positive, 0, negative. Okay? The most common type of AC signal is the wheel speed sensor. The wire is a 2-wire sensor, right? A positive and negative. As the magnet rotates around the stator, a voltage and current is introduced into the circuit. Now you can hook the lab scope to the positive and negative wires of the sensor. You get a signal like this. You can also hook it up to, you also can take the negative lead and hook it up to the ground of the battery, because sometimes it's hard to hook up the 2 wires to the sensor. So you can take the negative lead and hook it up right to the battery. Well, what happens is it will shift up a little bit, but it'll still be a pulsating signal. So what we see here is an AC signal. You see the 0 here is the middle line. Going all the way across to this end is 0, the midpoint. As it goes up, positive, it comes down, negative. The positive side is about a volt, a little over a volt, almost a volt and a half, and the negative side, this way, is about a volt, volt and a half. The total amplitude, but again, it's a known good waveform, it's an AC signal. The most common type is a speed sensor. It's a 2-wire sensor. You can have a pickup coil. Alright, and it's a pickup coil. And what else could be an AC signal? I can't think of anything else right now. Pickup coil, speed sensor. Oh, cam and crank sensor could be AC signals also. It can also be AC signals. Basically, AC signal like a little generator. A little alternator, right? That produces an AC voltage. Remember, the stator stays stable while the magnet rotates around the stator. That produces this type of voltage. Let's look at the next one. The next one will be, let's see. Oops, that's not the next one. What's the next one? Here's the next one. This is a, now the next one is a typical fuel injector, a saturated fuel injector. Okay. Here's system voltage, about 14 volts here. You can see this is the voltage scale here, 0 volts, 10, 20. It's about 14 volts here while the car is running because it's charging voltage. This is where the PCM driver pulls to the ground here, which is normal. On this portion here, this is what is held to ground. This is your pulse width. This is on time. This is probably measuring close to 3 milliseconds on time because the PCM is pulling the ground here and it's holding the ground. At this point, it's spraying fuel. So if I had cursors here, I would probably get, let me see, probably close to 3 milliseconds. So this is 2. So you can see here it's 2, 4, 6, 8. You're going to start about here to read it, the subdivision that we learned earlier. Okay, and it's 2 milliseconds here plus this. Yeah, it's close to 3 milliseconds. Okay, so right here, the on time is about 3 milliseconds. Okay, this is when the piece is holding to ground. At this point, this is when the magnetic field in the injector or coil collapses, and you get this kick. Now, you can tell how good the coil is according to this kick. Okay, every car is different on a kick, but a weak coil will produce a very low voltage. I might be down here to 40 or even 30, somewhere really low, either 40, 30 volts on the kick. It's indicated you got a partially shorted coil. Now, this is a good picture. Remember, these are known good waveforms. We're going to show you bad ones later on. So as it goes up here, it kicks and comes back down to system voltage. As you can see here, that little movement, that is the pintle of the injector closing on the downward side. When you see on this end, the pintle and the injector is actually closing. Movement. You want to see this on the saturated injector. If you don't see this, the pintle could be stuck and it can cause a misfire. And then we go back to system voltage. Again, this is a known good waveform, a saturated fuel injector. Now let's go to the next one. This is a peak and hold injector. You usually see this on throttle body injection systems like Hondas or anything that's a throttle body on it. They got this particular one's a peak and hold. They also have a peak pulse modulating type that looks similar to this. And what you see here again is system voltage here. The PC I'm pulling it to the ground, holding it to the ground, then turn it back off. Now on this particular injector here, we're sending about 4 amps of current to it to get it open with no resistor slowing it down. So we send about 4 amps to this to get it open really quick. Once it hits about 4 amps, it's actually going to switch it to another driver. Then you're going to be in this circuit here. That runs about 1 amp. Okay, so right here we got the system voltage, pulling it down, holding it open, then it's going to switch. Turn it off, then it's going to switch to a second driver. This piece actually has 2 drivers in it. So I got system voltage going to it, the piece pulls it down to get it open real quick. Once it gets open really quick, once it meets a certain amount of current, it switches from that first injector to a second driver. That second driver has a resistor in place and controlling the second half about 1 amp. Now the pulse width is from here to this peak here, always the last peak. Even for pulse modulating injectors, always the first drop, last peak. When you give it gas, this section stays the same. You will see this part increase and decrease the pulse width as you on this particular driver here. So again, this is called a peak and hold injector. This is a known good picture. Okay, again, I'm gonna repeat it again. We have this side at the first driver, right? When it reaches about 4 amps, it's switching from this driver to the second one. The second one has a resistor in it that works off about 1 amp. That second driver controls this pulse width here, this section here. My pulse width is from this drop to the last peak. If I give it gas, this section here will expand. On deceleration, it will close up. Again, a known good pattern of a peak and hold injector. Now, the next thing we see here is the primary ignition trigger. You can see here is my system voltage going to the coil. It's actually going to the negative side of the ignition coil. It's my system voltage here, and you can see the module, ICM, or PCM is pulling the ground. This is my dwell on time. Remember points? This is my on time. This is when the coil is being saturated at this point here. When it's near zero like this, you see the zero? When it's near this zero line, the coil is being saturated. When the module, ICM module or PCM releases the driver to fire the coil, you see this inductive kick going off the screen. Secondary ignition had the same kick but it's much higher. But this is an inductive kick after it fires the coil. Right here is my spark line, how long the spark lasts across the spark plug. Usually it's about 1.3, 1.5 milliseconds, depends on the car. And again, here we see our oscillations, our dissipating oscillations from the coil, and back down just below system voltage again. Again, this is a known good waveform from the primary ignition circuit. And the next one is a multi-strike Ford. This is earlier Fords. You can see here in green, system voltage again. Here's 10 volts, about 14 volts here. And we pull at the ground. But you can see in this case, it's been striked or pulled at the ground 3 times. 1, 2, 3. The only reason I could think they can do while they're doing this is maybe it's for hydrocarbons, emissions. At higher speeds on this particular vehicle, at a higher speed, this would actually go back to 1 strike. But at idle, you see these 3 strikes. Here, strike, again, pull at the ground, strike, pull at the ground here again, strike. Okay, this is a normal pattern on a Ford. multi-strike system on the permanent ignition. But remember, at cruise speeds, 2,000, 3,000 RPMs, it goes back to a single strike system. Okay, the next one we're going to talk about is the 4 crank sensor. You can see this is an AC signal also, permanent magnet. Now you can see here 0 volts because it's green, 0 volts. Now if you look at it, as the slide before, it was an even positive and negative. You can see this one is slightly shifted up to the positive side. That's because the battery, the lab scope is connected to the battery ground and not at the sensor, 2 wires on the sensor. That's why I shifted up like this. That's why I shifted up. But it's still a producing AC signal. You can also see this unusual gap here and here, which is one revolution. This gap is a missing tooth, and it's 60 degrees before top dead center. It's actually 36 teeth in this trigger wheel that passes the magnet, but one of the teeth are missing. So it's actually 35 teeth, 10 degrees separation, with one missing, indicating to the PCM on module that is 60 degrees before top dead center. So this is identified to either the PCM or module 60 degrees before top, 60 degrees, the piston is 60 degrees before top dead center. So it's designed like that. Again, this is a normal pattern. Now this one is this was a crankshaft sensor, permanent magnet. This is a camshaft signal, digital signal, Hall effect signal. Alright, it's a squirrel wave. Now you can see here a digital signal is a 3-wire sensor. Unlike this sensor, it's a 2-wire sensor. A Hall effect, a digital signal, aka a squirrel wave, is a 3-wire sensor. And uses the signal. It uses a power source, about 14 volts. It varies on cars. It's usually 14 volts, signal, and ground. It can be a pull up or pull down design. On this particular design, right, we start at 0. Okay, we start at 0 volts there. As the shutter wheel goes in between the Hall effect unit, right, it interrupts the magnetic field. The signal is then pulled up. Then when it passes, pull it back down. So high to low is 1 revolution of the camshaft. Then it repeats itself. Again, this is a normal pull-up signal. Hall effect signal, digital signal, I should say, for the camshaft. So this is a 3-wire camshaft signal, digital. Okay. Now what you're looking for is a nice corners, nice pattern, what you see here. So this is a good, again, a known good waveform. And remember, a Hall effect has 3 wires, and a permanent magnet has 2 wires. Now I have seen permanent magnet with 3 wires. The 3rd wire is like a shield for noise. Alright, let's go to the next one. Alright, next one is going to be, this is a 2-wire permanent magnet camshaft signal from a Ford. You can see it's a permanent magnet AC signal. You can see here this light, I guess you got light blue here, going positive about 1, it's about 1 volt, about 1.5 volts here. Then it comes, remember this is 0 here, and it comes back down 1, 1.5. So I got an amplitude of about 3 volts. Again, it's a known good signal of a 2-wire camshaft signal, right? This happens once every camshaft revolution. So it's a good signal here. So it went positive from 0, positive, and back down. Sorry, it went positive about 1.5, crossed the 0 line again about 1.5, going across here, right? Give me an amplitude of about 3 volts. Again, a known good signal, and this happens about once every camshaft revolutions. You can see right here going back down to 0 again, then it repeats itself. This next one is a idle air control motor Ford, which has battery voltage of 14 volts going to it, but it's ground controlled. You can see here, this is system voltage. You can see it's being pulled to ground. Now since it's ground control, if this increases, my idle increases. If it decreases, my idle decreases. It's all based on demand, right, at idle. Like AC come on, or deceleration, or you turn the steering wheel. I control my idle here. So I increase the on time, more air, higher RPM. I decrease it, lower RPM. Ground control. And it repeats itself. So this is a known good picture of an idle air control motor. This one here is a mass airflow sensor. Ford says it's supposed to be like 0.7, about 1 volt here, which you should look at. Then you're going to do a snap on a mass airflow sensor. What you want to do is snap it to see how it responds. A dirty wire will have less response than the good one. The voltage will be lower. So here, this is an idle car just sitting there idling, about 0.7 volts. Ford says 0.7 to 1 volt. I snap it. This here, this first peak and this little dip right here, and a sudden gulp of air or a slight vacuum being created. Vacuum differential being created here. That's normal. Here it's at wide open throttle. And this is what you want to look at. How far does this get? A dirty wire, or a defective mass airflow sensor, out of calibration mass airflow sensor, or a wire that has dirt on it. A hot wire that has dirt on it. That does not see the incoming air. This will be low in the specifications. Okay. Usually you want to see it go 3.5, 4. Alright, but current, if it has a current limiter on it, this might be a little lower. But it should be around 4. And you can see it comes back down again, back to idle. So it's a good picture of a mass airflow sensor. Alright, the response of a mass airflow sensor. Now this next one is say, from here to here, this next one is a Toyota crankshaft signal. Okay, which is a good signal. It looks unusual because you see it doing this. Okay, it gets bigger, smaller, and bigger again. And it can't top that center. Small, big. Now, usually in any other car, I would think this would be a problem. But on the Toyotas and the way it's made up, the material is made up, and several different reasons why, this is a known good signal, and the PC one had no problem identifying this signal, receiving this signal. Okay, again, it's a Toyota crankshaft signal, a known good pattern here. Now, we went from the Toyota crankshaft signal. Now we have the Toyota camshaft signal. Now you can see this is a known good waveform, digital signal square waves. You can see here we had 3 different sizes, but this is a good waveform. From goes up. Let me see. You got the wider one, medium, and small. This is it's almost like a 3x signal on GMs. And use the same method for identification. Now, also remember these 3 sizes are developed by either the shutter blade that's going inside the magnet, the Hall effect unit. Right, that's why 3 different sizes, because the shutter blades are actually 3 different sizes. It could be a magnetoresistive sensor or a photoelectric sensor. They have different slots with different sizes. That's why you see 3 different sizes. That's how 3 different sizes are developed. Again, they also use for identification. So this again a known good signal for Toyota. Now look at this Mazda crankshaft signal. This also a known good signal. This 5 volt signal from 0 up to about 5 volts. See here, 0 up to 5 volts. And what you're looking for is a nice square wave, which is good. But you can see here my 5 volts compared to my on time, my 0 volts is different here, and that is normal. So it's not at 50-50. It's not 50%. 50%. So it's not 50-50. You can see here it's different here and here, all through the whole pattern. But again, this is a normal signal for this Mazda crankshaft signal. Alright, here's a Mazda camshaft signal, a known good waveform also. You can see here we got 3 different square waves. different sizes, which is normal, right? And they use this for engine position. Okay, almost like a 3x signal in GMs again. Now, keep in mind, I'm going from 0 up to about 5 volts ground, 5 volts ground. And keep in mind, these 3 different sizes is created by either shutter blades, holes, slots, etc. That again, that's why 3 different sizes. And the PCM or ICM is using this for engine position. Again, this is a known good signal. I got 0 up to about 5 volts, pull back to ground. And a repetitive motion, repetitive signal again, just repeats itself. On this Mazda, 3 different signals. You can see here, medium, small, large. Medium, small, large. I said that incorrectly last time. Okay. Again, made up by 3 different size shutter blades, slots, or holes, or etc. It makes up these 3 different sizes. Again, they're made up from they're used for engine position, and it's a known good signal for Mazdas. I said it incorrectly last time. But this is 1, 2, 3. I said 1, 2, 3. It's actually here. Not paying attention to what I'm seeing here. Cause this almost looks smaller than that one. Yeah. Well, it's 1, 2, 3. Three different sizes here. Okay, which is again is a known good signal. Yeah. Yes, medium, small, and large. Now you look at this Mitsubishi crankshaft signal. This is a normal signal. Okay, 5 volts being triggered off and on. Different squirrel waves or / digital signals. Nice repetitive signals. This is a Mitsubishi crankshaft signal. Normal. That's a normal waveform here. Okay, the next one we're seeing is a Mitsubishi camshaft signal. Let's actually go with this Mitsubishi crankshaft signal. On this one, a known good signal also up to 5 volts. 5 volts being pulled down to 0. But you notice here we got a small squirrel wave to a large. Small, large, small. You can't see it, but it's large. Repetitive signals. This is a known good waveform. Again, for identification. So 0 volt, up to 5 volts, pull it down to 0. Repetitive signals, large, small, large, small. Normal on this Mitsubishi camshaft signal. It goes with this crankshaft signal on this one. Now on this one, it's a Jeep 4.0 liter crankshaft signals. You see these 4 sets of needles here. But they actually digital signal squirrel waves. And not a problem. What you're seeing is repetitive signals at right here, 200 millisecond time base. This will happen when you increase the time base. You see more repetitive signals, which is good because you can see the pattern repeating itself. But if I want to see just 4 of these by themselves, 4 signals or 4 digital squirrel waves by themselves, I would probably take this from 200 milliseconds down to 20 milliseconds. As you can see, just these 4. Now there's actually 2 crankshaft revolutions here. One revolution is a set, 3 sets of 4. So right here will be 1 revolution, another revolution. So this is actually 2 crankshaft revolutions. Again, a revolution is 3 sets of 4 squirrel waves, as you can see here. They're like needles, but they're actually squirrel waves, digital signals. It's just the time base is increased to make it look like this. Again, a known good signal. Now we're gonna look at this G 4.0 liter camshaft. We're going from 5 volts to 0 up to 5 volts again. This is a normal signal, usually located inside the distributor on this car, and help with finding injectors. This is 1 camshaft revolution. Low, high, 1 revolution here. A known good signal for this particular camshaft signal in this 4.0. You usually find this inside a distributor, and again, like I said earlier, it helps fire the injectors. Here's a 2005 Jeep crankshaft signal, right? It's also a digital signal. I could look at but you see alternating low, high, low. Again, the crankshaft position for the PCM. Just telling the PCM the crankshaft position. Alternating low, high, low signals. Again, a normal waveform. And the last one for the night is a camshaft signal. A normal camshaft signal for 2004 Jeep. Again, the telecomputer or ICM, the position of the camshaft. This right here, you see here, is normal. Right? Again, it tells the computer the position of the camshaft or engine position. This is a normal signal from 5 volts to 0, 5, 0, 5. A normal camshaft signal. Okay, thank you for watching that series of known good signals. Now we're going to show you on the next video, not this one, the next one, known good waveforms for a dual channel scope. Okay, I hope I see you in the next one. Peace. I'm out. I'm Nate. Alright, thank you for watching. That was on a single channel lab scope. The next one will be a known good waveform